Here we're looking at the warm-up from our 2.7 set of notes. We're asked to find the derivative of the following function. Now I've already gone ahead and graphed what that looks like. It's just a quadratic that's been shifted up 3 units. Now if we wanted to go ahead and take the derivative of that, we'd end up then with y prime is equal to 2x. And essentially we found the function such then that we can find tangent slopes at any particular target point. So for example, we could find what is the tangent slope, maybe specifically where x is equal to 1. Well, then you would just find that tangent slope by figuring out what that is when it's plugged in. So y prime is equal to 2 times 1. So it looks like that tangent slope would come out to be 2. And again, you could even just kind of see that from our graph. You can see that it's rising and running pretty much as a slope of 2. Now, the issue, though, comes where you're trying to determine what is the following derivative of, say, if you had a function like this. Well, again, if you're finding tangent slopes at a particular target point, I want to stress that it's a target point and not necessarily a target x value. So if we're trying to take the derivative with respect to x at like a value 1, notice that there are 2 y values. There's one up here and there's one down here. And that's why it's absolutely critical to actually have a target point, an xy coordinate point. Now you could still solve for y here by subtracting x squared over, ending up then with y squared is equal to 4 minus x squared. And then just take the square root of both sides. So the square root cancels out with your square, leaving you with just y is equal to plus or minus the square root of 4 minus x squared. And as a result, if you're trying to then determine what is your tangent slope at, let's say, this specific point, then you would only use the y value that has the negative. Again, because this positive one would represent this point. And that's why it's really important to have an xy coordinate point to then be able to throw that in there into the function and then see what is that specific tangent slope, not this one. So when we're talking about implicit differentiation, it's so important to actually have an x and a y coordinate point that you're actually looking at, because again, there are 2 of them. There could be even more than 2. There could be 3, just depending on what your function is. Now, implicit differentiation, again, is pretty much that case where there are multiple tangent slopes and you're really trying to actually like pinpoint the correct tangent slope. And that's why both coordinates are essential in finding that. Now, there are some steps as to actually how to conduct implicit differentiation. The first one being, you're going to take the derivative of both sides with respect to x. And then you're going to be treating y as a differentiable fraction of x. So what we mean by that is when you're trying to take the derivative of both sides, you'll literally end up with dy over dx somewhere in there. You'll end up then with the derivative of y as a differentiable fraction of x. So you should end up then with some dy over dx as a result of that. And then for step 2, the goal is to solve for that dy over dx. After you've solved for your dy dx, the third step is then to substitute in the specific xy coordinate point that you're hoping for that tangent slope. So you would substitute So you're again finding the tangent slope for that specific point. And then from that, you can find the equation of your line. Alright, so those are really kind of the base steps for implicit differentiation. We're going to be working with these quite a bit so that you guys master them. But again, that is the warm-up from our 2.7 set of notes.